Good morning. And we all know what a tiling is. This is a two prototile tiling, two types of tiles. It's also edge to edge. The edges fully match up. I've previously talked about fractal tilings that are single prototile and edge to edge. These have no gaps or overlaps, but they do contain singularities, points at which the density of tiles blows up, and they don't cover the entire mathematical plane. Now, most shapes will not fit together neatly like this. There's an example. But there are a number of them that do. Another example of that. And a couple more. Okay, a hyperbolic tiling is one in which the angle is something greater than 360 degrees at every vertex. And this is an example of a regular 7-gon, 3-gon tiling in the Poincare disk model of the hyperbolic plane. You can also try hyperbolic tiling in Euclidean 3 space. This example here by Edmund Harris is 7 triangles meeting each vertex. You get a kind of rumpled, chaotic mess. But you can also do these nice hyperbolic surfaces with knitting or crocheting. Gabriela Meyer did this one. So I decided to see what happened if I combined fractal tiling and hyperbolic tiling. And this is not any kind of rigorous hyperbolic geometry talk. It's just recreational mathematics. A lot of the driver is art. I'm interested in novel sculptural forms with geometric and organic character. So I'm exploring these with paper folding, computer modeling, and even clay modeling or clay sculpting. So kites and darts work well in the plane. Things are harder in 3 dimensions. Kites don't work so well. Darts work pretty well. Here's 2 darts together. In the V formed by one dart, you place 2 smaller ones, and you do these in pairs. You alternate buckling up and buckling down, and that's our rule. We're going to show an example here of a larger dihedral angle and smaller angle. This is actually the regular icosahedron angle. If we put a 3rd generation on that and do it in color, it looks like that. 4, 5, and 6 generations. And we go to 10 generations, we get something a little more interesting. There's some nice geometric character in the beginning, and then at the 10th generation, you've got a pretty organic, sinuous and complex boundary curve going on there. There's another view of that, and a 3rd view. You might think these are pretty exotic things, but actually in your local grocery produce aisle, there's a nice example of green leaf lettuce, which is remarkably similar. And kale is another leaf that's kind of fractal in character. So a problem with these is after a number of generations, 10 or so in this case, the smaller tiles interpenetrate the large tiles. And trying to avoid that, I went back and just looked at some planar fractal tiles and just said, let's just try to fold these and see what happens. So I'm going to take half of one of these. I'm going to move this vertex to make it more interesting. It'll be a 3, 4, 5 right triangle. So I'm going to use an alternating mountain and valley fold. This one's going to have 5 generations. These are on YouTube, including one I won't show today. It has a teaser. So that nicely folds up on itself. And the other geometry I showed there is the 30 and 120 degree angle version of the same fractal tiling. I'll do this one through 6 generations with the same alternating mountain and valley folds. And I'll iterate that digitally a couple times just to develop the fractal there. So, because these are in the plane, these edges hit each other and kind of stop you from getting a real hyperbolic vertex, if you wish. And you can't buy hyperbolic paper, but you can make it. So if you take 4 pieces, laminate them, they're drying there, and then we have a thing that's got 4 vertices with excess angle. And if we fold that alternating up and down triangles, you get something like that. Looks a little bit like the other thing, in general character. This is a similar tiling, but with trapezoids, and I'll do this one in Mathematica, so I've got the extra tiles there. I'm going to fold the 2 end trapezoids up and the middle one down. It does that, increase the bend angle. Looks a little bit like a leaf, a little bit organic. Increase the bend angle some more. And you're seeing this interpenetration problem showing up there. You can avoid that, it turns out, by doing a developing fractal curve. Jeffrey Irving demonstrated these first. This is a dragon curve. That's the first starting 2 lines there, and then next iteration, third iteration is here. You can join those with triangles, and you get a hyperbolic fractal tiling that will never self-interpenetrate, which is nice. It's got more than one type of prototile, and of course the boundary is just a planar curve, so it's not ideal in that respect. I first found out about these when I saw these 3D printed things that Henry Segerman designed. And I thought, this is just what I'm looking for, trying to do some ceramic sculpture. But I wanted to start with a circle instead of a line. And so I played around with a 4-hex. I found a fractal curve, which it turns out is in a Mandelbrot's book. And this is a circular, curvy version of that. And I thought about how to make a 3D thing out of this, and had some interactions with Bill Gosper and Neil Bickford that were helpful in doing that. There's just a print with the first 10 generations of that curve. So the sculpture is built up in layers. There's early on, a little later on. That's after the clay work is done, and after glazing. This is in the tea house yesterday, so you might have seen it there. That's the top view, which may look familiar if you're a member of MAA. And this, of course, topologically is just a cylinder. But you could imagine something where you start with a circle, and in each iteration, then you can add more circles, so it gets more complex. And that might look something like that. In other words, it's a branching fractal. And there's nature's version of a hyperbolic branching fractal surface. Okay, that's the end of that topic. My latest puzzle is called Polygony. It has 23 pieces. There are 4 solutions, and Bill Cutler was the first person to find all 4. And finally, I'm going to try the dice business with a tentative brand name of the Dice Lab. So Henry Segerman and I have worked together to design 5 dice that are currently in production. The star of the show will be a D60 with kite-shaped faces. When you put some thought into the numbering of these, we follow the usual convention where the largest number is opposite the smaller, the next largest opposite the next smaller, etc. And then we said, let's try to balance the numbers, and we decided that meant that the triples, there's 20 of these, should sum to the same number, as should the quadruples, or quintuples rather, and there's 12 of these. Henry did some computer search of some subset of the huge number of possible numberings and found an ideal solution where half the triples sum to 91, half to 92, half the quintuples to 152, half to 153. And I've got prototypes in case you want to see those. That's the actual size of the D60. There's 4 more, a deltoidal D24, a rhombic dodecahedron. This is a space filler, which is kind of fun. There's also a truncated octahedron. Numbers are only on hexagons. So all of these are basically isohedra as far as the numbered faces go, so they should be fair, of course. This can land on a square with a prototype that happens about 1% of the time. And there's a truncated tetrahedron. This has the advantage that the numbers face up. It's easier to pick up and also tumbles a little bit better. And that landed on the triangle about 3% of the time when I tested the prototype. And that's all I have to say. Thank you.